Lovely to be here. Thank you so much for a great welcome. My name's Mark Miodownik, and I'm a material scientist from King's College London. I'm going to take you on a journey tonight into stuff, into materials. It's going to be a journey into inner space. And we're going to find down there, we're going to find the secret to how jet engines work and how they are so amazing, and the taste of chocolate. You can't ask for fairer than that, can you? So look, let's go on this journey. I want to just show you what I mean. But before I do that, I just want to say to all of you here and all of you at home that in about half an hour's time through this lecture, we're going to do a mass chocolate tasting. Everyone in here is going to taste chocolate at the same time. Everyone at home is going to taste chocolate at the same time, hopefully. So if you're at home now and you want to join in, then you need to get someone to get you chocolate. You don't want to leave now because you're going to miss some amazing stuff. So go and find someone to get you chocolate. Shout out. Get someone to get you some chocolate. You guys in here, don't worry, because we're going to give you chocolate. So, are you ready? Let's go. So why don't I just start with some of the things that we are going to see. This just looks like any old liquid. Nothing that remarkable. Looks a bit like oil. Just a black liquid. But if we get a camera over here, I can just show you, look, there's a bit of black liquid. Now I put a magnet underneath, and suddenly it's a solid. Oh, a liquid. Oh, a solid. That doesn't seem right, does it? How weird is that? Now, I'll show you something even weirder with this liquid. Whoa. Now watch this, guys. I put this under here. Now there's a magnet on top of there. And if I wind this up closer to the magnet, oh, you see that? Now, they love the magnet. They love it. They love it so much they're going to try and reach it up. Look at that. And they're actually flowing up. Again, have you ever seen liquid flow uphill? How incredible is that? So this is a ferrofluid. It's stuffed full of magnetic particles. It looks like a liquid, but it's much stranger than that. It's stuffed full of little magnetic particles. I'll just let that go for a minute and show you something else, which is even stranger. How could something be even stranger than that? You ask? Good question. So let me show you. This is a piece of metal. It just looks like a wire, doesn't it? Nothing remarkable about that. But watch this. That's not right, is it? Now look, how can this be? Turns out that we've got some metal atoms in here, and we've trained them. That sounds weird, doesn't it, to train metal atoms, but they have been trained, and they've been trained to know who their neighbours should be, and so that they have a particular shape if they all get next to the neighbours in the right way, in the right orientation. But when I pulled it apart, I separated the right neighbours, so now it's not in the right shape. And I can jog the memory, I can let the neighbours get back to each other, and then recover the shape of the paperclip just by giving them a bit of heat. That's a bit of energy. They jostle around, they find the neighbour they want, and off they go. So watch this. Oh, it's crazy stuff, isn't it? So, this is the world. Oh, yes, come on. Let's hear it for me. This is the strange world I'm going to introduce you to, and it's just absolutely marvellous. Materials are marvellous things, and what makes them marvellous is that at different scales, so different sizes, they behave in completely different ways. And if you could start to understand that, you can do miraculous things like I just showed you. So I've started off with something really bizarre. Now I want to go to something that you know very well and seems kind of mundane, and I'll show you that even changing something mundane can do quite strange things. Okay, I've got a piece of iron here. Ooh, that's quite heavy actually. It's a big, thick piece of iron. I'm going to put some goggles on because over here we've got what is basically a giant Bunsen burner. And outside here we've got something called an air mover, and whatever I put underneath this will shoot it into the flame. You'll see why in a minute, because I don't want to do it with my hands. So, okay, so if we light the Bunsen burner, okay, brilliant, thanks Andy. Now, I put the iron into the flame and we'll see what happens, shall we? A big piece of iron into the flame. Okay, let's have it up. nothing happened, did it? Bit of an anticlimax. Okay, now I could have left that in there for an hour, a day, and this wouldn't have changed really. It would have got red hot, it had got a bit more rusty, and you know, nothing else would have happened. Okay, same material, iron, but this time in a powder form. Here we go, iron powder. And you might want to have a quick look at this. So just to prove to you, it's just a piece of iron powder, right? Now, so all we've done is change the size of this material. We've chopped it up into little iron filings, and now I'm going to put it in the flame. Yeah, I'm not going to put it directly in the flame because that would be a really bad idea. Now, how could this be? What's happening here? Well, what we've got is a very large piece of iron and a very small piece of iron. Now, in the large piece of iron, all the atoms, the iron atoms, are mostly in the middle of it. And the few that are on the outside, they can react with oxygen in the air, and they like to do that. But once they've reacted on the outside, they form a barrier, and so the ones on the inside don't get a look in, and everything just stops. Oh, let's look at these on. Let's put those there. But for the powder, all of the iron's on the outside of the powder. It's ready to react with the oxygen. So all you have to do is give it a little bit of heat. That sort of explodes. It opens up even more. That explodes some more. You get a mini explosion. And that literally is how fireworks are made. Different metal powders are in fireworks for different colours. It's not just true of iron. You can, if you reduce anything in size, it becomes more and more flammable. You can do this with custard powder. Honestly, you get enormous flames. Look at that. If you shrunk us down into a powder, we too would burst into flames. Okay, so just watch it on your old shrinking. So, okay, so that's what it's like when you make things small. Different things happen. But what is this world of the small that I'm talking about? And I want to just show you, because I've got a little microscope here, and I want to introduce you to this world of the small if you've not seen it before. Basically, anything you put it on, you can see. So here's the back of my hand. Oh, it's not so bad, is it? Here it goes. I've seen it many times, I know it really well. Here's if you think that's if you wait till you see this. This is what my face looks like. Come on, this is me, I'm in the room. Let's get off me. I'm so self-centered, aren't I? All right, let's get my shirt. Look, even something as simple as a button at this scale looks amazing, doesn't it? Wow. And this guy, Ted Baker, has obviously broken into my house and written his name on my buttons without me knowing. You've got to check these things with your microscope all times. Okay, look, so it's a wonderful place, this microstructure. So why don't we play a game? I'm going to show you the microstructure of some household objects which you know very well, but you've probably never seen them at this scale, and you have to guess what they are. How about that? Okay, so here's number one. Are you up for this? All right, just say nothing if you are. Okay. All right, here, what's this? That was the cloth. What's this? Go on, shout it out. Sponge. Okay, you guys are good. All right, I thought it was going to be... Isn't it beautiful, though, a sponge? Let me just show you that again, because I'm quite proud of it. Isn't that beautiful? Now, all right, here's another one. What's this? What's this? Ooh. Some sort of bubbles in some sort of surface. That's a kind of... What's that, a pigment? So what is this? Anyone? A cup. Fantastic. Brilliant. This is a teacup, a beautiful porcelain teacup. And those bubbles are tiny microscopic bubbles in the glaze of the cup. And the Chinese have spent 2,000 years perfecting that effect to give it a really beautiful luminescent feel. All right, so if you can understand these microstructures and you can change them, you can do fantastic things. They don't just look beautiful down here. The physics that dominates at the different scales changes everything about the material. So let's try and understand how physics changes with scale. And I want to do this with a game. One of my favourite games, and I've got a guess to play it with. All right. Yes. So, tell us a bit about yourself. What's your name?
Jamal Anderson.
And what are your basketball credentials?
I play for the professional team Essex Pirates and Great Britain under 20s.
I just wonder if you can do us a favour. Can you do a penalty shot? I know this is really under lots of pressure. The TV cameras are expecting all this, and you're not going to make it, I'm sure. But can you give it a go? Oh! That's impressive. Okay, now look, I'm going to change the game because I feel I'm at a disadvantage. What I'm going to do is we've made the hoop smaller and we've made the ball smaller. Now that should, in a way, make it easier for you, shouldn't it? So can you try and shoot a penalty now with a smaller ball? And actually, the hoop isn't that much smaller; it's lower. I mean, have a go. All close. You're good. All right, now let's make an even smaller one. Now I'm going to let you go a bit closer than here, but actually, literally, it's downhill all the way from your height, isn't it? And that should be peasy for you. And look, a tiny little ball. But it's not that tiny, unfortunately. You should come on, let's have a go at this. Oh. Well, look, thank you very much. That was really unfair of me, wasn't it, really? Because, he's used to playing with a certain size ball, but what we were doing is changing the size of the game, and we were changing the relative magnitude of two forces. One is gravity. So as the ball got smaller, gravity had less and less. It was exerting a smaller and smaller force on it. And the other was air resistance. So as the ball got smaller and smaller and smaller, its relative area got larger. So air resistance became a much bigger factor. And of course, it's very hard to calculate it when someone springs that on you. But this is in general what happens in life. As things get smaller, different physics dominates, and it changes the game. And I've got actually here. I didn't want to mention this other because I thought you'd just hit me. But I've got a tiny, microscopic basketball court down here. Look at this. And I was trying to play earlier on this. It's really difficult. Look at those balls. Aren't they sweet? Here's a tiny needle, which you might use to sew. Look how small the balls are in comparison to the needle even. Do you see how they're just sticking to it? They're just sticking to the needle automatically because at this scale, surfaces become very sticky. And if I try and bring them over to the court, the balls, and then I try and, all right, here we go. And I'm going to try and bounce them a bit. Oh, I can't even get them off the needle, and they just don't move, they won't roll. In fact, they won't bounce. It's just hopeless at this scale because the balls won't bounce because the surface forces, as soon as the ball hits it, just sucks it down. And gravity is so small on those balls that it's not exerting a great rebound force. So ants wouldn't be able to play basketball. Presumably they have other games they play with different rules. So is it true then that if we could understand the different physics at different scales, we could make some kind of crazy, interesting technology? Well, yes. Let me give you an example. You know what it's like when you're going for a walk, and it's a summer's day in Britain. You put your coat on, of course, because even though the sun's out, as soon as you put your coat on, the clouds come over, don't they? And the rain starts to fall, and then the wind gets up, doesn't it? And you're walking, you're still enjoying yourself because it's a lovely day and you're getting a lot of fresh air, but then the leaves start falling on you, but it's okay because it's really good to clear the head, isn't it? On a good winter's day, and then you're like, okay, I've had enough. I've had enough. I've had enough. Some things stick to you in those moments of sort of weird summer walks. Look, I've got one here sticking to me, and it's these weird burrs, and they kind of weirdly, amazingly sticky things, but they don't seem to have glue on them. So how do they work? If you're a material scientist, the first thing you do is get your microscope out and you have a look under the microscope at them. Can you see these weird little hooks? Isn't that amazing? And it's those tiny little hooks that get into your coat, and what they're doing is they're latching on to a piece of wool or cotton, and that's the stickiness. And it's really very, very effective. And of course these have evolved to stick to animals' coats and to spread the seed of the bird tree. But could we use that to make a sticky technology that would be useful? Perhaps we could. Well, a guy called Georges de Mistral, a Swiss engineer 50 years ago, had the same idea. So in case you're thinking of going out now and patenting this idea, you're too late. In fact, you're so late, I imagine that almost all of you, in fact, I guarantee all of you have a piece of this technology in your house, and maybe, probably, on you now. Has anyone here got Velcro shoes? You have? All right. Would you mind coming up, just showing the shoes? Okay, yeah. Hello. What's your name?
Rosie.
Rosie. Oh, Rosie. Now look, Rosie, this is going to sound like a weird thing to ask you, but could you take off your shoe and show it to me? Is that going to be a danger zone or not? No. Okay, brilliant. Okay, fantastic. Okay, do you mind just have a look at it? And you can come and have a look at it too under the microscope. So here we go. Now let's have a look at your Velcro shoes under the microscope, and let's see what we see. Well, we see a range of hooks. Look at that. And that's just loops of nylon. Can you see how they've been made? Nylon has been cut in the middle. Does that make sense? And so it's those little hooks that are mimicking the hooks of the burr. And the other side of the Velcro is here, and it's just a bit of kind of nylon mesh. See that? The other thing is it's kind of infinitely reusable. It records your life in a way, because it stays with you such a long time. For instance, it picks up bits about it. Look down here. See, look. That tells me that you used to have a boyfriend who had a red sweater. Am I right? Am I? No. Well, look. Thank you for being a great sport. And you can go back to. So we can stick small things, bags, shoes, and it's really convenient. On, off. You don't even have to look at how it latches. But can we stick big things? How big can we get? Outside we've got the biggest piece of Velcro we could find, and we've got 2 volunteers to help us try it out. Okay, you ready? What's this? Okay. Thanks, guys. So look, once you've got the hang of this Velcro thing, you sort of think, wow, we could really do some great stuff with this. Why don't we scale it up? Let's have massive, giant Velcro. Well, look, for the first time ever in the Royal Institution, we've got giant Velcro. And we thought, well, let's try it out. So I need 4 volunteers to help me with this. Yes, okay, brilliant. What about you? Yes. And you there. Yes, you. And all the way, yes, you. Yes. This could be a new step forward in technology. So what I'm going to try and do is we're going to try out this giant Velcro. So it's a bit heavy, and there's 2 handles here. Do you think you two could manage that? Is that all right? Is that not too heavy? And you guys, you've got actually the heavier bit. Sorry about that. Are you all right there? Fantastic. Okay, right. Now look, we've exactly scaled Velcro up proportionally. So these 2 bits and the thickness and the length, everything's the same. Let's see if it works. Okay, off you go, guys. In the middle. Yes. Now that should have stuck. So we'll test. Pull it apart slowly first, just to see. Yes. Okay. Well, that sort of works. Fantastic. So the first part of Velcro works when you scale it up. Now the genius of Velcro is that you can unstick it easily, right? So let's try and unstick it easily. You try and tear that way. That's not really working though. That's to pull out. It's still there. Okay. Okay, guys, put this in the middle. If you just put that down there in the middle, yeah. Fantastic. Okay. Thanks very much, guys, for trying out the gel vocal. Thanks very much. Yeah. Okay, so look. The unsticking doesn't work very well when you scale it up. Did you notice that? They had to actually use their hands, which would be difficult if you were doing it with your own little unstrapping your shoes. And why is that? Well, we've scaled it up exactly. So we've got scaled up all the material dimensions. And actually, when you scale up nylon, which is what it's made from, this is what you get. This stuff, and it's actually not very flexy. It's quite stiff at this scale. And so the genius of Velcro is that when you're unsticking something, the little heads, these things here, they flick back really easily. If you have a look, you'll see that they flick back really easily. And that noise it makes, that scratching noise, I'm making it now, like that. That's these little rods vibrating after they flicked. Right? So that's where the sound comes from. In fact, did you know that the military have silent Velcro? Yes. Interesting, isn't it? I mean, you can sort of expect that. But so look, the thing is that you can't just scale things up and expect them to work, because the physics changes, and the physics we're relying on here was elasticity, and actually by scaling up the dimensions, that didn't really do us any good. So sticking works, but unsticking doesn't work. Let's think about delving even deeper into this microstructure and looking at different forces down there and seeing what else we can manage to do. And I've got something here that really is marvellous, and it's at a much smaller scale than Velcro, and it's on this little tiny silicon chip here, and it's a machine. It's called it's a little MEMS machine, microelectronic device, and it's it's smaller than the width of a human hair. So even though I'm showing you this little device here, but there's no way you can see it. We need a really strong microscope to see what I'm talking about. And it just so happens we've got one. We've got an electron microscope outside which uses electrons to see instead of light, and it can see incredibly tiny things. Fantastic. This is great. Hello. So this is an electron microscope. This is John.
Hi, Mark.
Hello. And this is Kelly, who's doing the tilt. And we've got one of these machines inside this microscope. It's in there. So it's on a sample holder, and it's deep in this machine. And this is the visual output from the machine. So John, what we've got here is I'm right, just to get the scale, isn't it?
Yeah, we've got one of your machines. We planted it in this field of Velcro to give you some idea of the scale. So you can see the Velcro hooks here. As we take the mag up, you can see we've got another scale.
So this is Velcro, and we're zooming in to see the machine behind it. And what else is behind it?
Oh, well, that's a head louse.
A head louse?
Yes.
So that's what we've... A knit, is it?
A knit, if you want, yes, if you must.
They were the bane of my childhood. They used to fall out of my... So can I see it face to face? I've never actually seen one face to face. It looks like a weird kind of cactus. Look at that.
So if you look here, human hair would occupy this sort of space.
Right. So this thing's about the width of a human hair.
Yeah, it's about twice the total width of a human hair.
Amazing.
Because it has to grip.
Yeah.
So it puts its legs around and grips the human hair.
It looks like these weird hairs all over it. And behind it is the machine we're talking about. It's this type of micromechanical machine. Wow. Look at those holes. So these are all moving parts, aren't they?
They are indeed.
Yeah, so this is a machine that moves, and its features are 1,000th of a human hair width.
Yeah.
Around?
These holes are about 5 microns. So.
Absolutely amazing to be able to make machines at this scale, don't you think? Smaller than the hair on a kind of head lice. That's incredible. So why would we want to make machines this small? So you're all used to smartphones and tablet computers that do cool things, like they change the screen to suit which way up you're holding it, right? So they basically know which way up is. Now that's really cool, because this is an electronic machine, but it knows which way gravity is pointing. Now, how can you do that if you're an electronic machine? Well, the basic principle is this. You have some sort of rod and a mass. And if it's in this orientation, you know which way gravity is because it's down. If you turn it, the rod bends because of the mass. And so now you know that down is that way because it's deflecting that way. So what these things do is that if you measure that deflection, you can know which way down is. So you do that, it goes that way, and you do that, it goes this way. So essentially these, what are called accelerometers, they measure forces, and they measure the direction of the forces acting on it. And in the case of gravity, that's very useful to know which way an image is up. So I want to show you what the accelerometers in these types of machine look like under the microscope. Okay, you can see it's made out of silicon, and the great thing about making it out of silicon is it's integrated into a silicon chip, so it works at a scale where electrostatic forces are dominant. But the change in the electrostatic forces, because these two things are nested together, so that if they separate slightly because they've changed in orientation, because you've turned it, the small amount of electrostatic charge that changes is very easy to monitor. So it's not just that it can do cool things for you, it can save your life too. Wow. Okay, fantastic, a little car. So, what's this got to do with it? Well, this was my first ever car. Well, it wasn't really, but anyway, I wish it was. I wish I had been that kid. Okay, now in the front of all cars, every car that's made now, and in the front of this car, which has been retrofitted, is one of those accelerometers. And it's measuring forces, right, by weights moving around and the electrostatic forces in it. And that gives a readout, a little electronic readout that goes into this silicon chip here. So there's a computer in your car, and it reads out the forces from the accelerometer. So this car knows what forces are acting on it. So I'll show you, we've got a readout of the accelerometer. If I hit it there, you can see a little force is registered on there, right? You're wondering what that red line is. We've set that red line as the maximum force this car would like to have on it before it thinks it's in a crash. So below that, there we go, a little one like that, and it's not going to deploy any safety measures. If it hits a big force, it thinks we're in a crash, I better deploy some safety measures to save my passengers. Fantastic. Shall we try it out? Now, I think what we want to do is sort of set this car on a kind of collision course with a wall. Maybe there. Are you guys okay with that? Are you? You want to stay there? Can I ask you guys to move out over here? Is that all right? Just for the moment. And you'll get a better view of the crash, honestly. Right, fantastic. We've got our crash site already prepared. Well, it wouldn't be a real crash unless we had a passenger, would it? Are there any volunteers? Yes! Okay, good. A good volunteer, fantastic. Let's have a round of applause. Okay. Crash test dummy. Clunk, click, every trick. You don't hear that these days, do you? All right. It's now... Oh, I've got that wrong. Okay, let's put over the shoulder. Right. How are you feeling? What's your name? Should have asked you that earlier, shouldn't I? Crash test dummy. I don't think you're a dummy. Okay, fantastic. Crash test dummy's in place. Okay, here's the arming button. This is so James Bond. Arming the safety measures. Okay, it's armed. You want to do a countdown? 5, 4, 3, 2, 1. How are you feeling, okay? A bit shocked? I know. Fantastic. Oh, yes. Right, off we go. Anytime you see something really amazing happen, really think, at what scale is that thing happening? And it's almost the magic that you see around you, these airbags, these incredible materials, these Velcro, the magic's in the microstructure. And you really want to think about what we can do with microstructure to make amazing stuff. If you could have anything made, any piece of magic made, right, what would you like? Being able to fly, we can do that. Jet engines, anything else?
Time travel.
Time travel.
Invisibility.
You want invisibility? Okay, I think we can do invisibility. In fact, people have already made prototype invisibility shields. I'm going to show you one in a minute. But first of all, let's just work out, if you wanted an invisibility cloak, how would it have to work? What would it do? So let's say I got a cloak and I was going to be invisible. Right? I put it on to me. Right? I'm standing here and I want to be invisible. So anyone ahead of me has to see all the way through me. So they have to see this desk behind me. So how's that going to happen? Well, the light coming from the desk is going to have to hit the invisibility cloak. It's going to have to be diverted around the invisibility cloak, right? Bent around it. And then it's going to have to come out as if it had never hit it in the first place. So the key to invisibility cloaks is bending light around the cloak and then setting it on its way again in the right direction. If we can do that, then we can make an invisibility cloak. So how do we bend light? It's something that seems remarkable, but you're sort of used to it, I think. So here's a tank of water. So, imagine that you're sort of having a drink, you've got a straw and some lemonade, and you put it in, and you're used to this, right, aren't you? In it goes, right, and it seems to have bent. So how does light bend? Well, and it turns out that light travels at different speeds in air and water. In fact, light travels in different speeds in all materials. And the measure of that is called the refractive index. And if two materials have different refractive indices, then when light goes from one to the other, it bends. Okay, so the key to bending light, to understanding how to bend light, is the refractive indices. And this is different for every material. So if we can manipulate refractive indices, we can start to bend light to our own will. Now, I want to show you something weird about bending light. But first, I need a volunteer. Fantastic. Now, I haven't chosen anyone in the middle over there. What about you, sir? Right bang in the middle. Oh, yes. Fantastic. Hello, what's your name?
Darius.
Darius. Okay, fantastic. Now, Darius, before we do this demo, I want you just to look into this and put your hand. Are you happy putting your hand into a bowl of water?
Okay.
Are you happy with that? Yeah?
Yeah.
I want you to just put it in here and just check there's nothing in there, okay? Oh, you're saying there's something in there? Well, if there is anything in there, take it out. Ooh, who put those in there? That's incredible. It looks like there's nothing in there, doesn't it? Why don't you put those in there and we'll see if they disappear again. Ooh. Okay, do it again. Oh, look at that. So this bowl is full of those. You just can't see them. Isn't that incredible? You can just put them back in there, yeah. Go on, have a go. Well, thank you very much. Now, look, before you go, I just want to ask you, do you have any idea how that works? Have you got some ideas?
Not really.
It's a tough question. It's something to do with the refractive index, isn't it?
Yeah.
Good answer. Brilliant. You are good, you. Okay, thanks very much for that. Okay, so how did that work? Well, if light bends when you have two materials with different refractive indices, if you can match the refractive index of the balls with the water, then light won't bend. And that's exactly what we've done there. Right? We've got some balls with exactly the same refractive index as water, so light just goes straight through it. And because they're transparent, you see nothing at all. I mean, it really is effective, isn't it? But that's not going to work for an invisibility cloak, because we don't want the cloak to be transparent, because then light would just go straight through it. So we want something that bends light, but isn't transparent. And I've got an invisibility shield here. This is one of the first prototypes ever. So material scientists have made this invisibility shield, and it actually works. Let me show you how it works. So light comes in here, it gets bent round, and it goes out there. Or light comes in here, it gets bent round and it goes out there. Right? So whichever angle light comes in, it gets bent round and it goes out the other side. So anything in the middle is invisible. You will never see it. That's incredible, isn't it? Now, how does that work? Obviously, we're manipulating the refractive index, and I want to show you a picture of it up close. So there are these tiny, microscopic little interventions in the microstructure which allow us to change the refractive index, manipulate it at will to allow light to bend. Now, for this shield, it only works at microwaves, which are longer light waves than visible light. So this won't work for visible light, but it will work for microwaves. So if you were to put a cup of tea inside that little circle and put it in the microwave, it would never get hot, right? Because the microwaves would hit it, be bent round, and never get to the tea. I know, why would you put tea in a microwave? It's much better to use a kettle. That's not the point. Okay, so if we could do it for visible light, how would we do it? Well, it turns out the visible light's much shorter than microwaves, so we need much shorter microstructural features. But the principle is exactly the same, and people are working it all over the world, I can tell you. In fact, I think there might be... sometimes I see things out the corner of my eye, and I sort of think someone's already done it, you know? No, anyway. That's just a... But this is what it would look like, isn't it? If I got an invisibility shield to work, you'd also have to solve the problem of having it flexible. But then, once you've manipulated the microstructure and got the refractive index right, you put it round you like this, and then you could just sort of say, well, imagine your teacher's coming and you haven't done the homework. You just go, I'm invisible. And you should... This is going to really change the game of hide and seek fundamentally, isn't it? Yeah. Okay, so these things are going to happen, honestly, in the next 5-10 years. You're going to see these things, which is incredible to think, isn't it? So far I've talked really in this lecture about us manipulating microstructures to do weird things, magic things, which are great. But nature itself does a lot of strange stuff that is just magic, and to understand that, we really need to understand what happens when we go even smaller and see how individual atoms fit together. So I've got a liquid here, and the molecules in this liquid are just milling about, doing not very much. It's transparent liquid. But if I pour it, it does something a bit odd. It turns into a solid, and it won't stop doing that. We're going to... And now it's just growing. Look at this. And can you see these crystals growing? Isn't that incredible? So this liquid is turning into a crystal as we speak, just like that. What are crystals? Because we hear a lot about them, and, you know, it's good to think about them a bit. So this is what we think of, isn't it, when we think of a crystal? Something with kind of these faceted sides, and it might not be as big as this, it might be a diamond ring, it might be a ruby necklace. These wonderful, translucent, transparent crystals. And they do marvellous things with light, they do marvellous things with electric fields, all sorts of crazy stuff that they do. You know, you can make lasers with them. So the crystals clearly are special materials. And what is a crystal? Well, it's an arrangement of atoms. And we saw with that liquid, it's weird because the liquid had no structure, and I poured it in, and then suddenly it got a structure. It remembered, oh, actually, we all want to be regularly arranged in a crystal. You go there, you go there, you go there. And who was telling them? Well, no one was, but they just did it. And they arranged themselves in these regular arrays. And if I show you this, you can see that crystals there are lots of different crystal types, and that's why there's such a wide range of them. And they have these remarkable, sometimes if you can line the atoms up and you get these directions where all sorts of things happen. They're fantastic things, but the one thing they don't do very well, they don't really kind of cope with, is you hitting them. They're sort of not so keen on that. Well, let's just confirm that, shall we? Crystal, hammer. Hammer meet crystal. couldn't we make a crystal that could withstand impact and that you could bend? Wouldn't that be great? Well, they exist, and they're called metals. So look, this is what you normally think of as a metal. It's just a sort of rather grey, unremarkable, maybe brightly coloured thing. But if you look inside it, right, that's what metals are like. Okay, so if I now go back to this, right, we know what's going to happen because we've all done this to metal. But let's just reiterate that. I put the metal in there, I whack it with a hammer, and actually I'm making huge dents in it. It's not just blobs of matter are moving around, right? It's that crystals are deforming, changing shape, but everything on that impact is still crystalline. They are one of the most special crystals around, and this is how they bend. And what you're seeing here is this is a crystal, metal crystal, and these are dislocations. So they're defects in the crystal. And I'll show you one in a minute. And these things can move. In fact, they're always moving around. And you'll see in a minute there, do you see it go? And that was under a bit of stress. So the person under the microscope was stressing the crystal, and this thing moved. And that moves one piece of the crystal from one side to the other. Here's what they look like, right? So you can see this is a crystal. It's a metal crystal structure. But you can see that there's a defect there, right? If I line it up properly, there's a defect, right? Now, under stress, this whole top of this crystal can move, and it only requires a small amount of energy to shift the whole crystal all the way along. And so that means that metal crystals can change shape in real time at the speed of sound. A crystal that you can hit, you can bend, and it moves. It reorganizes itself. So metals are great because you can mold them at high temperatures, and then you bring them to our temperature, and they're really hard and tough and fantastic materials. You make cars out of them, aeroplanes, cans. The only problem with this whole scenario is that there are times when you want the metal crystals, to survive at very high temperatures, right? Like in a jet engine. Now, jet engines are not cool places at all. I'm going to show you how kind of powerful jet engines are with this clip. So this is a 747 with 4 jet engines. Now, you'll see in a car, the engines are on, the car moves across, the power out of the back of the engine, it pushes the car, okay? That's a lot of force that's coming out of that engine. They're amazing things. They're absolutely astounding things that we've invented. And what's happening at the back here is a turbine spinning around, and they look like this, these turbine blades. And they're spinning around at really high temperatures. And these metal crystals are called superalloys. And the reason they're called superalloys is because there's only one metal that can survive these conditions, and we were so impressed with it, we called it super. I'm not joking you, that is really the why the name is called it. So these things are called superalloys, and they're an incredible structure, and they survive high temperatures, but also high stresses, because it's zooming around really fast. And I want to just remind you why zooming around, right, why rotating is such a difficult thing to cope with. And I've got a guest to help me just show you that now. Okay, this is Sean. Give him a big round of applause. Sean has agreed to help me with this demo, haven't you?
Yes.
Because I just want to talk about why rotating something, so a blade, in the case of a turbo jet engine, is so high stress. And first of all, we're going to do it, and then we'll talk to Sean afterwards about how high stress it was. Are you all right with this? Okay, you ready? Okay. All right? Ready? Okay, go. Run. How are your arms?
I feel very stressed.
They feel stressed, don't they? I know. And imagine that was, thousands of revolutions per second. How much more stressed you are? How would that feel?
They'd probably be feeling like they'd fall off.
Yeah, exactly. No, it would be terrible, wouldn't it? Yeah. Anything else you want to say about this?
I enjoyed it.
Oh, fantastic. Well, that's great. Thank you very much for coming on. Thank you. Okay, so we've got these turbine blades whizzing around at really high stresses, really high temperatures, and they've got to not break. And this super alloy is the alloy for the job. And I know that you're thinking, well, why don't we just use steel? Steel seems great for everything. But super alloy is so much better than steel. And I want to show you how much better it is for this job. Please welcome another guest. Who are you then?
So my name's John,
Yes.
and I work at the University of Cambridge, and I'm a material scientist trying to make super alloys even more super.
Great, fantastic. You're the man to talk to. So what have we got here?
So here we've got a piece of steel, just a normal piece of steel, and then here we've got a super alloy, which is a state-of-the-art super alloy. And so what we're going to do is we're going to have a materials head-to-head, and we're going to hang some weights on the end of each of the materials, and then heat them up with a blowtorch, and going to see which is the better material at high temperatures.
Okay, great. So yeah, goggles on. So the weights go on. And yes, you've got steel, haven't you? And I've got
steel,
super
and
alloy.
you've got super
I like
alloy.
it that way around. So they're the same thickness, they're the same volume,
Exactly.
and this is the blowtorch. Blowtorch is on. Okay, great.
Okay.
You ready? So let the challenge begin. Okay. I think we could just be here all day with the super alloy, couldn't
we could.
So that, you know, in case you were thinking steel is the latest thing that you would want to put into a jet engine, super alloy is just so much better than this job, isn't it?
It is indeed, Mark.
Well, look, thank you very much for coming on and showing us that. So I said super alloy is so great, but I didn't tell you why it was so great. And of course, you know the answer, don't you? You know the answer. The magic's in the microstructure, of course. So let's have a look at the microstructure of this super alloy. And actually, this looks like a weird image, but I'll just talk you through it. So these little funny things, they're those dislocations. So they're the fault lines in the crystal. And they're the things that let the crystal move and change shape. And in the case of the super alloy, we don't want that to happen at high temperatures. So we want to stop them moving. And these things here are little crystals within a crystal. So you've got crystals growing within crystals. This is a bit like a sort of traffic system in a city. And they're only letting the dislocations run down these little alleyways here. They can't get through here. And this means that they all get jumbled up and they find it very hard to move, and it's gridlock. And as the temperature goes up, the gridlock doesn't get released. And that's the trick. And the higher you can get the temperature, the more efficient the engine. And the more efficient the engine, the less fuel it uses and the more power it has. So it really is absolutely vital, not just in terms of safety, but efficiency of engine and power to get this microstructure right. Okay, so that's how we design microstructures that won't melt at high temperatures. What if we want to design a crystal that will melt on demand? Well, we can do that too. In fact, you know all about it. You eat it every day if you're lucky. It's this crystal in chocolate. And the whole point of this crystal is to melt only when it gets in your mouth. And it's a billion-dollar industry making crystals that only melt in your mouth. Let me just kind of gear us up here now and say that we're going to do a mass taste testing of chocolate. Great. At home, I hope that you've got some chocolate ready for this taste test, and if you haven't, now is your chance to try and find some. And what we're going to do is Chris is going to taste chocolate at the same time that you're going to taste chocolate, but he's going to do it in a very special way. He's going to get into this dentist chair. I hope that's not going to alarm you too much. And we're going to put an endoscope into his mouth, or a camera inside his mouth, so you can see, while you're eating the chocolate, you will see him, what the chocolate's doing inside his mouth. You've never done this before, have you? Yes. This is a whole new chocolate experience. All right, ready, everybody? We're about to do this. So get ready to put this in your mouth. Get ready not to chew it, but just to let it melt in your mouth. Are you ready, Chris? I'm going to give it to you. You can put it in your mouth. Okay, pop it in your mouth now. Mass taste testing in the UK. Now, what's happening is you've got this kind of waxy solid in your mouth, and it seems to be doing not very much. If you explore it with your tongue, you'll find it's a bit cornery. It's a bit of a taste of corner, isn't it? But as it stays in there longer, it's starting to melt. Yes, you're getting a little bit of melting going on. And what that is the cocoa butter is melting. It's a crystal, and it's melting on your tongue. And when crystals melt, they're taking energy from your tongue because they need it in order to melt. And that's called the latent heat. And that will cool your tongue because you're taking heat away from it. Only you feel it, well, don't say, but you should be feeling a cooling of your tongue now. Oh. And now, after that, once it's liquid, it's going to start to release the flavour molecules. And there are about 600 different flavour molecules in chocolate. And actually, they're going to go up the back of your mouth into your nose. And that's where you're going to start tasting the chocolate. Because that's the real richness in your nose, is where the taste is coming from. And in a minute, I'll tell you what they are, those molecules. But also, what's now happening in your mouth is the liquid is releasing the sugar crystals that have been embedded into the cocoa. And that should be making its way onto your tongue and making it feel sweet now. You should have a sweet sensation. And now there will be other things like a sort of slightly milky dairy sensation because of the milk protein and powder in your milk chocolate. And at this point, there's chemicals like theobromine going into your blood from the chocolate and caffeine. And they're starting to make their way around your body. And they're going to go into your brain and give your brain a bit of a buzz, a nice pleasant buzz. All the while, the mass of chocolate on your tongue is getting more and more molten, more and more delicious. It's smelling more and more lovely. And you should start, if you can really look out for the really fruity flavours, because these come from the fermentation of the beans. The beans are left in the tropics on the floor to ferment. And then also you should feel this kind of... there'll be a lot of caramelly, nutty, roasted flavours coming from the roasting process of the chocolate. And this is such a rich, wonderful flavour. It's just the most glorious thing. Now you've got this mass of hot chocolate in your mouth, haven't you? And what you want more than anything else is to glug it down, don't you? And put it down the back of your throat. Are you ready to go? Okay, so now just let that mass of chocolate. Yes. It's a really physical experience, isn't it? Okay, let's give a big round of applause. Here we go. This is a little model of the microstructure of chocolate, which you just ate. I'm just going to talk you through it. So, a lot of what chocolate is fat, a really delicious fat called cocoa butter, which you can also use as a cream. That's what creams are. And here it is, we've got it here, and it exists in 6 different crystal types. And each one of those crystal types has a different melting point. And of course, if you have the type that's too low a melting point, it will melt in your hand, or it will melt in a shop, or it'll melt on not a very hot day. And if you get the type that's wrong, it will never melt at all. So you need to get type 5 crystals. Also, we've got the cocoa solids from the beans. This is where all that kind of wonderful flavour comes from, and all the roasting, all the caramel, and all the nuttiness. And we've got some milk protein solids, and we've got some sugar. Okay, so those are the main ingredients in chocolate. And of course, when you put it on your tongue, it's very strange. It's a very strange object. Anyway, I can't explain it. It's very odd. But anyway, there we go. Right now. So you put the chocolate on your tongue. Ooh. Ooh. And you can see immediately that what the fat is doing is not only is it controlling the melting point, it's also controlling when these other ingredients are released. So you want that fat only, A, to encapsulate them, to protect them, but B, to kind of also then release them at the right moment, and just when it gets into your mouth. And then, of course, it becomes sort of very creamy, and all of that rest of the stuff that you experience happens. Now, this is a mock-up of it, and we'll see in a minute what happens to this. But I want to show you the real microstructure under the microscope. And we've got a microscope outside, so let's go and have a look at it, because it's not often you get to see chocolate under the microscope. So I'm just going to nip outside and have a look. Hi John, hi Kelly again. Okay.
And we're using a detector now that responds to the density of the material. So the denser the material, the brighter the image. So you can see here where we've got some very bright crystals, those are sugar. And with the fat globules here, we can even see that there is a difference in brightness or darkness, whichever way you like to look at it, between them, which shows that they are different materials.
Yeah.
Some is cocoa butter and some is other.
So we've got some sort of other fat in there, these globules, haven't we?
Yeah.
It's not all pure cocoa butter, and it's very kind of heterogeneous. It's sort of all mixed up,
it's very
lumpy. Yeah, lumpy. That's a good word. Okay, so so that's what chocolate looks like under the microscope. You saw it there, and this is what these are those same ingredients that we've kind of made into this model, and you can see now what's happened. That the fat has melted, just like we all just experienced. It's an incredibly sophisticated material, this, as sophisticated as steel, and yet tastes a bit better than steel, in my appearance. So that's the amazing science of chocolate, and how it works at the micro level. But there's one last thing I want to explore. And so I want to play a game with you about microstructures, and I want to sort of see if you can tell the difference between living and dead microstructures. So microstructures in living things versus microstructures in non-living things. And I've got a few examples for you. So I'm going to put them up on the screen and you shout out whether you think they're living or dead, okay? All right, you ready for this? So is this from a living or a dead thing? Well, quite mixed, aren't we? Quite mixed. This is actually living. This is from a plant. All right, this one. Dead? You think is this like an electronic machine? Do you think? It's a fly's eye. Fly's eye. I've got this other microscope here which I want to show you, because I want to show you that it's still, even at other scales, it's hard to tell the difference. So what do you think this is here? Is this a living or dead? You fell into my trap! No, because it's artificial skin. It turns out that once you go to this inner space of materials and you start looking around, as we've done, it is actually quite difficult to work out what the difference between living stuff and non-living is. And essentially, it's not that easy. The physics is the same for both the living and the non-living, right? But living things can do some things that are just miraculous, that we would like to be able to do. And one of them is, it can make self-healing materials. So we all got skin that if you cut it, it will heal itself. And I'll show you of course what this, you remember, so you get a gash and then it looks horrible, but a few days later it's healed itself. Now that's brilliant. Wouldn't we all love that? Because you're all used to, maybe accidentally breaking your mobile phone one day, and you think, wow, that's A, it's expensive, and B, you think you've got a relationship with this machine, and it knows all your secrets, right? Or you bump your car, it's a small crack, the insurance company doesn't agree, but anyway, and wouldn't it be great if your car could just heal itself? This is the thing. Wouldn't it be great if we could make self-healing materials for mobile phones, for cars? Well, it doesn't seem so impossible, does it? Because you sort of know that living materials do it, and the way they do it must be to control the microstructure, and they must be regenerating the right microstructures. So if we can find a way of controlling and regenerating microstructures, we could do it, right? So here's some samples of a self-healing plastic. And these early samples are rudimentary, but let me show you how they work. So this is inside the microstructure of that plastic. A crack comes down here, so that it's getting injured, and it hits these little capsules here. Now inside there are little capsules of resin, which is a liquid, and it flows out into the crack, and it heals the crack. And it does that because it reacts with a catalyst, which makes this liquid resin become a solid. So it's a bit like blood clotting. It sort of stops the problem. And of course, it doesn't go, in this case, it doesn't go back to being as good as it was before, like our skin does, but it's progress. It doesn't seem too much of a stretch to think that we could also, if we could get materials to self-heal, that we could also crack this idea of what life is. Because living organisms, they don't seem when you look at them and you look at them under the microscope, they don't seem like they're doing anything magic. They're just manipulating the microstructure really cleverly, and they're regenerating microstructure really cleverly. So we could do that. We could make artificial living organisms if we could just understand these processes better. And I'm absolutely sure in this century that's going to happen, that we'll make artificial life, and instead of having buildings that are static, or mobile phones that are static, or bridges or roads that are static, they'll be living, they'll heal themselves, they'll reorganize themselves. And it could be one of you who does this. It could be one of you here who develops that technology. And I really hope it is in 20 years' time that one of you is standing here telling us about that. I just want to sort of say one more thing, which is to remind you that the magic, whenever you see the magic, all these new gadgets are going to come out, when the invisibility shields come out in 10 years' time and you buy one, I want you to go, I know how this works. The magic is in the microstructure. So thank you very much for listening and for enjoying.
And the last of our lectures is here on BBC 4 tomorrow at the same time. Coming up next tonight, an incredible feat of mass engineering in Wellington bomber.